This is Math156, third script for week 11 on confidence intervals for proportions. This is based on example 7.17 in the textbook, and in addition to reading that example, you should review the third page of the math notes. This is the situation where we have a pivotal statistic, but we have neither a location parameter nor a scale parameter, and the analysis leads to some very messy high school algebra, which culminates in using the quadratic formula to solve a quadratic equation, and I'm going to use the solution to that quadratic equation to do my simulation. So here's the scenario. Suppose that the true parameter of the percentage of the population that favor the death penalty for murder is 68%. We poll 1,308 people and ask them, and of course we get something which is drawn from a binomial distribution with 1,308 trials, a probability of success of 68%, and if we divide the number of people who answer yes by 1,308, I got 0.668. Of course, if I do this over and over again, I'll get a different number every time. In the example in the book, the number they used for x was 899. Okay. Now I'm going to use this yucky algebra, and I'm not going to bore you with the mathematical details here. Go back and look at the math notes. What we want to do is compute a 90% confidence interval, so we're going to calculate from our observed proportion two quantities L and U, which have the feature that the probability that the true proportion is less than L is 5%, that it's greater than U is also 5%. Now, from all these various numbers, the quantile that I calculated from Q-norm using a normal approximation to the binomial distribution and the p-hat from my sample, I get the solution to the quadratic equation. That has one term plus or minus another term, center plus or minus spread. Center minus spread is the lower limit on our confidence interval. Center plus spread is the upper limit. And what we expect is that 90% of the time the true proportion will lie in between these numbers. Like most of these useful tests, this has been thoroughly automated, so you don't have to understand why it works if you just want an answer. It's called prop.test, and it calculated 0.668, 0.710. Let's go back and look at what we got. 0.668 and 710. It's always reassuring to discover that you can do by hand exactly what R does in its automated tests. Now we'll do a simulation of it. 1,000 times we will generate a sample from this binomial distribution, compute center and spread from p-hat, compute L and U from that, and if the true proportion P is greater than L and less than U, we were correct. So we'll count 1. We expect that'll happen 90% of the time. And let's plot some line segments for the first 100 trials and look at what we've got. So when you look at this, on each line, the red is the percentage of people who answered yes. The horizontal line goes from L to U. What we expect is that the true proportion, 68%, will cut the horizontal segment 90% of the time. There it is, shown as a red vertical line. And out of our 1,000 trials, we found that 90.7% of the time the true proportion lay in between L and U, which is exactly what a confidence interval is supposed to do. And that's all there is to this little video.